This is Ecopolis. In this groundbreaking six-part series, Nobel Prize-winning scientist Dan Kamen reveals the technology that could transform our cities and usher in a brighter future. This episode, energy.
Cities are critically dependent on their energy supply. If we don't have a reliable, safe, clean source of energy, the cities can't function.
Using Ecopolis as a testbed, Kamen investigates new cutting-edge technologies.
The time is now very short. We have to get the right technologies developed, deployed, and into place. We're going to have to start now.
He hopes to discover those technologies that can revolutionize our future and save all the world's cities from possible disaster. Ecopolis, population 18 million. By 2050, experts predict 75% of us could be living in cities exactly like this. A typical Ecopolis citizen will use 3 times as much energy as today and generate 5 times more carbon dioxide emissions. The environmental damage could be irreversible. The biggest challenge facing our planet today is to find clean and reliable energy solutions that grow alongside our cities.
Cities of the future could use 5 or 10 times as much energy. More people, more technology built in is going to make the overall needs of those cities very, very challenging.
Professor Dan Kamen is investigating futuristic energy solutions from 4 visionary scientists. His task? To clean up the polluting energy sources that power our cities today. Burning fossil fuels for energy is the biggest man-made cause of carbon emissions. There is an existing low-carbon power source, conventional nuclear fission, but accidents like Chernobyl and the problems of keeping nuclear waste safe cast a long shadow.
The lurking problem with nuclear plants today is that if there is an accident, if there's a nuclear meltdown, it's a major event. It's not a small industrial accident. It can change the landscape. It can change cities. It can change your entire country. It's a big, big issue that we have to come to grips with.
Now, a bold technological solution offers a safer way to harness the power of the atom. It recreates one of the most powerful forces of the cosmos here on Earth. But it uses only tiny amounts of fuel to generate almost unthinkable quantities of energy. Professor Chris Llewellyn-Smith is director of a multi-billion-dollar experiment that could one day free us from fossil fuels and old-style nuclear energy.
I will be much happier about the long-term future of the planet if I knew that there were other options out there. And there is another option, it's fusion.
Nuclear fusion. For 50 years, it's been the dream of energy experts. A safe, clean, and cheap means of unleashing massive amounts of energy. It's the process that lights up the sun and all the other stars in the universe. The question is, can we recreate this miracle of the cosmos right here on Earth?
It's really a matter of getting all the different technologies and systems to work at once and see if we can get them to work reliably.
Ecopolis, a typical megacity in 2050. Experts believe that if we don't change our polluting ways, it will be hell to live in, and we will cause irreversible environmental damage. Dan Kamen is part of a team of Nobel Prize-winning climate change scientists. He thinks green technology could head off an energy crisis in future megacities. From 4 ideas, he must choose a single technology with the best chance of saving Ecopolis. Deep in the English countryside, at the Jet Laboratories, an international scientific team is aiming to match the sun's awesome power. Meet the tokamak. It cost $1.5 billion, and it's the largest prototype fusion reactor in the world. Within this donut-shaped chamber, they're attempting to capture the power of the stars. Stars like our sun burn hydrogen in giant fusion reactions. To recreate fusion in the lab, scientists need special types of hydrogen that will fuse more easily. The good news is that sources of this fuel are so commonplace, you can find them in your own home. Tritium, extracted from lithium, a common metal used in batteries. While deuterium comes from ordinary water. Nuclear scientist Mark Burskins is confident these simple ingredients are the key to our future energy needs.
Take all the lithium that you can find in a laptop battery. The lithium-ion batteries contain about 6 grams of lithium. If I take that and produce a tritium from that, and combine that with all the deuterium you can get from a bath full of water, then you have enough fuel to provide a normal person for a lifetime with electricity.
In theory, 1 truckload of this fuel could power Ecopolis for a decade. That would mean a lot less nuclear waste than conventional fission, and just a tiny fraction of the hazardous radioactivity.
With a nuclear fusion plant, you do end up with nuclear waste, but it will only stay radioactive for a short time.
But cooking up a fusion reaction is far from straightforward. The sun, nature's ultimate power station, is a giant fusion reactor. It's made of plasma, a glowing sea of electrically charged particles, mostly made up of hydrogen. Deep within its core, gravitational forces crush the plasma and heat it to 27 million degrees Fahrenheit. Under these extreme conditions, hydrogen particles crash into each other and fuse, creating a new element, helium, and releasing enormous amounts of energy. There's no way to match the scale of this process here on Earth, so scientists must find another way. The answer is to turn up the heat, and that is the job of the tokamak. To kickstart the reaction, the jet team drives temperatures to an almost unimaginable 270 million degrees Fahrenheit, 10 times hotter than the sun's core.
So in fact, we can say that here on JET, we reach the highest temperature in the solar system.
Maintaining such extreme temperatures is a huge challenge. The scientists must ensure the plasma doesn't reach the steel sides of the tokamak. If it did, the heat energy would dissipate, stopping the reaction dead in its tracks.
This is a plasma here. This is about 1,000 degrees. And why doesn't it get hotter? Because actually the plasma particles hit the wall and then they cool down.
The jet team cracked the problem using another fundamental force of nature, magnetism.
I can shape it in many different shapes. And if I do it properly, then I would run the magnetic field along the tube and I could keep the particles away from the wall. And that's how we confine the plasma in a fusion reactor.
Inside the tokamak, powerful electromagnets control the plasma, drawing it away from the sides of the chamber and maintaining the superheated state that triggers fusion. The jet scientists have successfully created a fusion environment, but they are still perfecting the process. They monitor the action from the control room. It's like having a window into the center of a star. They power up the giant magnets, inject the plasma, and fire up the tokamak. The superheated plasma particles zoom around at 10,000 miles per second. They smash into each other and fuse. Just like in the sun, this creates helium and a colossal amount of heat energy. This is nuclear fusion, right here on Earth. It's an incredible scientific achievement that could change the way we think about nuclear power forever. But there's a hitch. Within seconds, it's all over. Keeping the burning plasma in place puts tremendous strain on the magnetic coils. And if they get any hotter, they'll melt. So the tokamak can only run for around 30 seconds. The jet team can create the power of a star, but they can't sustain it. So far, it doesn't run long enough to pay back the energy it consumes.
Where we are today is that a jet has produced 16 million watts of fusion power, but it took about 25 million watts to run it.
To solve the problem, 34 countries are throwing $13 billion into ITER, a giant tokamak 10 times the size of the jet reactor. ITER's super-strength magnets will contain the plasma's heat more effectively and withstand higher temperatures.
In the future fusion device, we will use superconducting coils, and these don't overheat, they don't need to be cooled. So in fact, you could run the pulse much longer than you can here a jet.
The payoff, ITER should generate 10 times more power than it consumes. And by 2050, scientists believe fusion may be powering the world's megacities.
In something like 30 years, plus or minus, we will have, I'm reasonably confident, power going into the grid.
It could be a dream solution for Ecopolis. But it's up to alternative technology expert Dan Kamen to decide. It's a tough call. He can only select one of the 4 ideas presented. To help him decide, the Center for Alternative Technology, a scientific think tank, has calculated how far each idea would reduce the megacity's carbon footprint. The first option is nuclear fusion. Will it launch a power revolution? The calculations reveal an extraordinary result. If fusion reactors supplied all our power, it could be a golden ticket, wiping out all our carbon emissions in one stroke. There's just one snag. Fusion scientists still have to make it work on a big scale.
The issue facing fusion is, can we make it work? Fusion is a high payoff, high risk operation. It's a technology that if we can make it work, it's got a great upside, but if we don't make it work and we've spent a great deal of time and money, then we're stuck.
And even if scientists can crack it, Kamen has other concerns. In an uncertain future, relying on any centrally generated form of power could be a big mistake.
As cities become larger and larger and the populations increase, their supply lines become longer and hence more vulnerable to disruption.
The weak link is the infrastructure bringing power into the city. But the next idea could see city dwellers generate more of their own energy. A technology that literally floats above rooftops. A mini levitating power plant for every home, inspired by a futuristic train. Wind power. In rural areas, we've been harvesting it for millennia. But in cities, buildings obstruct wind flow, making it harder to capture that energy. So wind turbines in cities are a rare sight. Canadian Jim Rowan is on a mission to change all that. Rowan's a former radar specialist turned maverick inventor, and he wants to use our city's rooftops to capture wind power.
Everybody has a roof, and every roof can have a wind turbine on it. And if every roof has a wind turbine on it, the amount of electricity we can make is absolutely astounding.
Most experts dismiss city rooftops as not windy enough to power turbines. But Rowan was sure he could beat the problem. First step, simulate wind patterns around city homes. This experiment demonstrates what Rowan calls the roof effect.
As the air comes towards this house here, it doesn't go around the house, but rather it goes over top of the roof of the house.
There's no shortage of wind at the roof's apex, but the air becomes turbulent, spinning off in different directions. Even flat roofs disrupt wind flow the same way. And conventional upright wind turbines can't handle this kind of chaotic wind flow.
The roof distorts the wind. If wind strikes the turbine from more than one direction, then the turbine has aerodynamic stall and it won't function.
Rowan decided to go back to basics, scrap the old-style windmill design, and create something totally new.
It actually came to us in about an afternoon of furious design work. The turbine shape itself was a bit of a eureka moment.
Rowan's new turbine rotates horizontally. Its blades are designed to capture wind from any direction and at lower wind speeds than conventional turbines.
The wind is only hitting it at about 1.5 miles an hour. The interesting thing about this is it can take wind from all different directions at the same time.
The prototype turbine should harvest every last scrap of wind energy. Now, Rowan is building a version for a household that should test it to the limit. Meet energy-guzzling Doug Fowler and his family.
Our electricity is actually calculated, I believe, on an industrial rate because of our high usage. It actually equates to about 4 houses.
As technology use soars, experts predict that by 2050, every household will consume nearly this much energy. But satisfying the Fowlers' energy demands won't be a breeze. Their home isn't in a windy spot.
We're putting a large blade configuration on Doug's house to generate electricity in a very minimal wind area. If we can generate 5 kilowatts of electricity on a regular basis in not such a great location, we should be able to generate this kind of electricity in better locations.
The Fowlers appear to need an extra big turbine, but that would create noise and vibration, presenting Rowan with his next engineering challenge.
The problem that you have with putting a wind turbine on the roof is vibration. Not only will it keep you awake at night, but it could actually cause your roof to collapse.
The problem threatened to derail Rowan's vision, until he found inspiration in an unlikely source. A high-speed train that levitates to reduce onboard vibration. The German maglev.
If you could levitate a train, you should be able to levitate a wind turbine. So we started down the path of finding the best way to levitate our wind turbine.
The maglev floats on giant magnets, an elegant design based on simple science. Every magnet has 2 poles. Opposite poles attract. Just like the maglev, Rowan's turbine exploits the reverse magnetic force. When 2 like poles face each other, they repel. As they get closer, the electromagnetic field that pushes them apart is so powerful, it makes Rowan's turbine platform, with a load of 5 people, literally float in thin air. It's friction-free, which should hugely reduce vibration and noise. The day of installation. A levitation base and other key components slot into place. Rowan delivers the test turbine in person. The team raise the sails 60 feet onto the barn roof.
That's good. Keep it going.
The turbine slips into place
There you go.
and starts to spin. It works. The levitating turbine has no direct contact with the roof, which means less noise, virtually no vibration, and no roof collapse. But how does a floating turbine convert the energy created by its spinning sails into electricity? Once again, Rowan's solution uses magnetism. A set of magnets rides on the turbine's outer rim, and a loop of copper coils sits in its base. As the turbine spins, the magnets pass over the coils, generating electric current. It's ingenious and efficient. Rowan must wait and see exactly how much electricity his turbine generates, but he is convinced it marks the dawn of an energy revolution.
What I'd like to see is a wind turbine like ours or somebody else's design on every single roof, so that there can be local generation for people.
City skylines have acres of empty roof space. Could this vast area be put to better use? Energy expert Dan Kamen must decide whether to back the idea. The news from the carbon counters won't exactly blow him away. They estimate that in a city like Ecopolis, it may only make a tiny 0.13% dent in CO2 emissions from energy.
The mag-wind technology got a very low score, and I have to admit, I'm not all that surprised by it. This is because urban areas are just not great sites to harvest large amounts of wind power.
Kamen thinks it could be a great technology in the right place, but not in Ecopolis. Yet its core principle has huge potential.
Scaling up the mag-wind design is very attractive because as you get to higher elevations and higher altitudes, you get to a very much larger and richer wind resource.
His instinct could be right. Inventors are racing to utilize high-energy, high-altitude wind from way above the clouds. But the next carbon-saving idea has already scaled stratospheric heights and helped us explore a faraway planet without ever setting foot on it. Ecopolis, a fast-forward vision of a typical future megacity. By 2050, its population is forecast to more than double to 18 million. Green whiz Dan Kamen fears soaring energy demands are a ticking time bomb.
Without a reliable and sustainable source of energy, cities just simply don't function. And cities of the future with 10 or 20 million people couldn't possibly exist.
He believes future cities will need a reliable source of green energy that never runs out. That source could be Earth's cosmic neighbor, 93 million miles away. A non-stop, virtually limitless powerhouse of energy and a space-age capturing device. This man believes that we can access enough energy for all the world's megacities, now and in the future. Australian John Lassick is passionate about photovoltaic technology, solar cells, devices that turn sunlight into clean electricity. For decades, Lassick has been on a quest for the ultimate solar cell.
For us, the genesis of module development really started with this little single cell device here. This was actually built about 20 years ago in my backyard. This little unit put out about 7 watts at about half a volt.
7 watts will barely power a light bulb, but Lassick was determined to find a way to tap the potential of his sun-kissed homeland.
Australia has an excellent solar resource. About 80% of the country is desert. So if you look on the bright side of that, we've got a lot of solar radiation.
In a single summer's day, Australia receives enough solar energy to power the entire planet for 6 months. And solar cells are already a tried and tested technology. So why not carpet vast areas of land, clad all our buildings, and pave every street with them? The problem is, conventional solar cells are just not cost-effective. They're made of expensive silicon, and a staggering 90% of the energy that hits them is simply lost.
The efficiency is relatively low, around about 10% system efficiency. When you look at the traditional forms, such as a coal-fired power station, they might have a range of 25 to 35%.
Lassick realized if he could find a way to concentrate the power of sunlight, he could produce much more energy from fewer solar cells. His breakthrough? Using mirrors to focus the power of the sun. This is a scale model of one of his concentrator dishes.
What we're looking at here is an array of curved mirrors that focus all the light that falls on this plane to the receiver. At the focus of the dish, there's an array of photovoltaic cells which convert that intense energy directly into electricity.
The full-size concentrators are 50 feet across and carry 112 mirrors that track the sun as it travels across the sky. The mirrors collect sunlight to focus energy onto a tiny square of solar cells. But these are no ordinary solar cells. To realize his vision of super-efficient solar power, Lassek needed something special. The answer lay 60 million miles away, on the red planet. In 2003, NASA dispatched 2 high-tech remote-control robots to Mars to analyze soil and rock samples. The only practical energy source for the Mars rovers was the sun. But Mars receives just half the solar radiation we get on Earth. NASA's only option? To adopt a new ultra-efficient solar cell design to capture all the available solar rays. Sunlight is made up of photons, tiny packets of light packed with energy. When these photons strike the silicon in a solar cell, they knock free electrons, producing electric current. But conventional solar cells only absorb a fraction of the available power. For the Mars rovers, NASA turned to a cutting-edge invention: solar cells with multiple layers made of special materials, each one able to absorb a different frequency of sunlight. They take a bigger bite of the solar spectrum, capturing photons that would normally escape, providing the rovers with 3 times more electricity. The super-efficient cells looked ideal for Lassek's solar concentrator. But his troubles weren't over. Lassek's mirrors are so effective at directing sunlight that just 2 of them can ignite solid wood within 3 seconds. An entire dish multiplies sunlight 500 times, focusing a beam of light that can reach a blistering 1800 degrees Fahrenheit. Enough to instantly incinerate Lassek's high-tech solar cells.
We're in an environment where the solar intensity is 500 suns. That's enough to melt steel. So it's necessary to manage that temperature in order to keep the cells happy and have them run for a long time and very efficiently.
Lassek overcame his final hurdle by developing a patented system to extract heat and keep the cells cool.
It's an ultra-high efficiency heat sink, which is capable of keeping those cells at less than 60 degrees centigrade.
After 20 years' hard work, Lassek's groundbreaking solar concentrators are up and running in Alice Springs, Central Australia.
The breakthrough that we've created is to develop a solar panel that is 1,500 times more powerful than a traditional solar panel of the same size.
A single 50-foot diameter dish generates the same power as 3,500 square feet of traditional solar panels. And now, Lassek is building the next generation.
Right now we're rolling out the world's biggest photovoltaic power project, 150 megawatts in the northwest of Victoria.
The solar plant promises to power 45,000 homes. It will wipe out almost 400,000 tons of greenhouse gas emissions every year.
We're targeting a cost around about the same as you can buy traditional power at, around about 10 cents per kilowatt hour.
Sun-drenched Australia could have been designed for solar power. But what about countries with less sunny climates? We may not have to wait for the sun's rays to reach Earth. One day, solar space dams could track the sun to beam back vast amounts of solar power to receivers back on Earth. One thing seems clear: we are finally learning to harness the biggest energy source in our solar system. Could efficient solar concentrators cut the carbon footprint from energy use in Ecopolis? Turns out they knock a surprisingly modest 13% off carbon emissions, highlighting a thorny problem with all solar power. When the sun goes down, so does the power. But Dan Kamen is confident that scientists will find a way to store solar power.
The batteries we have today are okay. They're not all that cost effective, but they do the job. And if we were to focus effort in this area, to store energy in a variety of forms, I think this is an easy problem, one that we just have to give some attention.
If science can fix the storage conundrum, concentrators could supply all future energy needs without any emissions. Cadman has explored 3 technologies that could consign fossil fuels to the history books. But the final technology could let us carry on burning our coal and oil reserves without damaging the environment. A system that uses high-tech alchemy and deep underground prisons to transform coal into a clean, green fuel. Meet John Caldy, a scientist with a no-nonsense take on our energy dilemma.
Stop using coal? We've got thousands of existing power plants generating nearly all of our present-day electricity. What are we going to do, mothball those? No, we can't.
But there's a problem. Coal is the most polluting of all fossil fuels. Every year, a typical coal plant produces 10,000 tons of sulfur, causing acid rain. 10,000 tons of nitrogen, the pollutant responsible for lung-burning smog. And, worst of all, a whopping 4 million tons of CO2, environmental enemy number 1. And that's from only one plant. Caldy thinks there is a way to carry on burning coal with a clear conscience. By capturing the carbon dioxide it emits and burying it deep underground. Loy Yang Mine, Victoria, Southeast Australia. The biggest coal mine in the Southern Hemisphere. Its power station chews through 65,000 tons of brown coal a day, releasing the same amount of CO2 as 60 million cars. Physicist Paul Ferron is working on a pilot scheme to capture that carbon dioxide, the first critical step to making it safe. He's perfecting a system to remove CO2 from the power plant's flue gases.
What you're looking at here is a microscale version of a real CO2 capture process. So it has all the elements of a real-life plant.
Flue gases from the power station furnaces pass through a solvent containing special molecules called amines. As the CO2 bubbles through, it binds to the amines. Next, the solution is heated to 250 degrees Fahrenheit, breaking apart this bond. The amine gets recycled to perform the same task again, while the CO2 is compressed and cooled into a liquid. So far, so good. But the process uses a lot of energy, so the power plant must chew through more coal, making it less efficient.
If you reduce the efficiency of a coal-fired power station from 40 to 30%, that means that you need to use 25% more coal to produce the same electricity.
Ferron needs to make carbon capture more energy efficient, or power stations just won't use it. His strategy is to make his solvent mix the most effective CO2 extractor in existence, removing 90% of it from flue gas without using large amounts of power. He's running tests at an experimental unit attached to the Loyang power station. It's like mixing the perfect chemical cocktail. Now, after years of trial and error, he's close to the ideal formula.
We've tested over 100 different chemical absorbents thus far. So ultimately this goal of 90% CO2 capture and maintaining your energy efficiency at say 40% is not that far away in my view.
Other carbon capture systems require big changes to power stations' infrastructure. But Ferron's system can be retrofitted to existing plants.
This technology is the only technology which you can use as an add-on to existing power stations and will allow you to reduce the emissions.
But efficiently capturing carbon dioxide is only half the battle. Finding places to store millions of tons of this stuff securely is a big challenge. Scientist John Caldy's grand plan is to put it right back where it came from, more than a mile beneath the Earth's surface.
The carbon comes from the ground and all we're doing is putting it back where it originally came from.
It's crucial that the CO2 stays underground. If it reaches the atmosphere, it would make the whole process an expensive waste of time. Caldi needs to be 100% sure none will escape. And now, he thinks he's found an ideal test site. The Otway Basin in southern Australia. 6,500 feet below ground is a rock formation that once stored large quantities of natural gas. The rock layers here are impermeable. They imprisoned the gas for millions of years until it was discovered and drilled for fuel. It's the perfect carbon lockup.
And now we're using that same formation that the gas used to be in to inject the CO2. The beauty of this is that we know that there's enough storage volume so we can put the CO2 in.
The final destination for 100,000 tons of CO2. A sandstone layer with millions of tiny pockets. Ideal for trapping gas. Above, a harder layer of rock acts like a lid to seal the CO2 in place. The monitoring team wants to see how it behaves as it settles. Caldi's confident it should stay down there forever.
Should there be any kind of untoward movement of the CO2, we will know about it well before it ever gets to the surface.
Scientists estimate that around the world, there's enough space to bury at least 1 trillion tons of CO2. And with 150 years worth of coal still in the ground, it's a technology that could help bridge the energy crunch.
What we're trying to do here is put together a technology that is transitioning from the time that we're relying on the coal-fired power plants to the time that we can actually go to renewables. And that's what carbon capture and storage is all about.
Experts predict that by 2050, megacities like Ecopolis will rely on coal to generate their power. Capturing and storing the CO2 it emits could be a neat solution. It's up to climate change strategist Dan Cannon to decide. He's no fan of fossil fuels, but he can't ignore the numbers. Capturing and storing carbon could slash an extraordinary 83% off carbon emissions from energy.
As much as we'd like to make the transition from fossil fuels to renewables, our economy runs on fossil fuels today, and that means it's going to be with us for decades to come.
It's a tough call. Pitched against 3 other cutting-edge technologies, can carbon capture win out? It's crunch time. Which technology will Cannon choose to save Ecopolis, future megacity? Dan Cannon, Nobel Prize winner and top government energy advisor, is investigating 4 carbon-busting technologies to help us survive the future. In the year 2050, our virtual megacity, Ecopolis, will be struggling with a fossil fuel hangover. Its cause? Too much pollution from high energy consumption. Energy use has a devastating impact on global warming. Cannon must select a single technology to clean up our energy supplies. It's a big decision.
Cities of the future face a number of problems, but energy is at the top of that list. They need a secure supply, it's got to be clean, and we have to get those technologies developed and deployed. Time is very short. We're going to have to start now.
In Australia, John Caldi is working on a solution to clean up coal. Stripping CO2 from power stations and locking it away deep underground offers an astounding 83% carbon saving. But Cannon's not sure that a fossil fuel makeover is the best approach.
Carbon sequestration also opens what I would consider the slippery slope problem. We're not going to capture the carbon from all of these, which means that we might be building more of a fossil fuel economy right at the time when we want to get off of these and transition to renewable energy sources.
In Canada, inventor Jim Rowan has developed an ingenious levitating turbine designed to capture the power of the wind as it flows over cities. It may score only a tiny carbon saving, but Kamen is convinced that wind power as a resource has a lot of potential.
I really like the idea of the MagWind. It's a very attractive technology, but doing this on every single rooftop with lots of little machines, I'm not quite sure that's going to pan out in urban areas where there's just not that much area to harvest wind from.
It's time for a tough decision. Carbon capture and the MagWind turbine offer different avenues to the same goal, the transformation of Ecopolis.
Our energy problems are so big and so extensive that I'm disappointed to throw away any technologies. I am, however, going to have to do so for both the carbon capture and this particular wind technology because they do have a number of drawbacks.
2 out of 4 technologies remain: solar concentrators and nuclear fusion. Australian John Lassick started out designing solar cells in his yard. Now his company's concentrators capture enough energy to power entire communities. But without a scientific breakthrough that cracks the storage problem, solar power only scores a 13% carbon saving.
Solar energy, as a major part of our energy future, needs to have ability to store that power at night when the sun is not shining down on a given area. That means the batteries of today have to get better.
If batteries do improve by 2050, solar energy score soars to 100%. Nuclear fusion doesn't face the same challenge. Because it doesn't capture the power of the sun, it creates it. In the UK, Professor Chris Llewellyn-Smith and his team believe it's a solution that will provide us with unlimited energy. But nuclear fusion is a high-stakes gamble. It's still only an experiment. And for now, it eats more energy than it delivers. The scientists believe that by 2050, they can turn fusion around. If they succeed, it will score 100%. But does Kamen agree?
The problem is, to develop it's going to take a lot of money and a lot of time, and it's a real gamble. The best technical forecasts for when fusion would be available are 2040 or 2050 at the earliest. That puts us in a risky situation if we're going to wait for this technology. Do we get it done in time? Is it available when we need it? I'm just not quite sure.
If they reach their potential, both solar and fusion promise to wipe out all energy-related CO2 emissions in Ecopolis. But Kamen must choose only one energy technology to transform Ecopolis from a city in crisis to a model metropolis.
I'm very reluctant to pick one or the other between solar and fusion.
But thinking time is over. Is it solar concentrators or nuclear fusion?
In terms of a single technology to be a winner, I'm going to go with solar. Solar energy is a fantastic resource. Every second, thousands of times more energy hits the Earth from the sun than we consume as a human society overall. That's the winner.
Dan Kamen's decision revolutionizes Ecopolis. It starts to generate its own electricity, not by burning fossil fuels, but from a shining array of hundreds of super-efficient solar concentrators, all tracking our brightest planetary neighbor. The unimaginable power of our nearest star delivers a cleaner future for generations to come.